Hello Westview, this is problem 7-9 for chapter 23 and 25. We'll be primarily looking at electric potential and electric field in this problem. So, part A wants us to draw arrows at points L, N, and U, as you see I've done here, that indicate the direction of the electric field. Simply put, you have to memorize that electric field always acts perpendicular to these, which are equipotential lines. When you draw your arrows, make sure they're at right angles. Nothing fancy. Part B wants us to find at which of these letter points is E greatest in magnitude, or where is E the strongest in magnitude. So recall that the definition of an electric field is negative dV over dr. In other words, where is the electric potential changing the fastest? Electric potential changes the fastest when equipotential lines are closest together, in comparison to dr. You will notice out here that equipotential lines are actually quite far away from each other. That means E is rather weak out here. Here, on the other hand, E is very strong because electric potential is changing extremely fast over here. That explains why, of course, T is the answer to B, as T is where the equipotential lines are densest. Part C wants us to get an approximate value for the magnitude of E at point P. So E is dV over dr. That means we're going to have a reference point in which to change from that reference point to P. In this case, we would choose the 30 volt equipotential line. So the change in the 30 volt equipotential line to the voltage of P is actually 30 minus the voltage at P. The voltage at P, well, you'll notice that P is right in the middle between 30 and 20. So the number right in the middle between 30 and 20 is 25. Thus explaining why dV is 5 volts, of course. For the change in R, the change in R from the 30 equipotential line to P is indicated actually by this little measure down here. So we know that dr is actually 10 to the negative second meters. Thus, all we have to do is put 5 over 10 to the negative second power. So E equals 5 volts over 10 to the negative second meters. Thus, we should end up with 500 volts per meter. Okay, so part D wants us to find the approximate value for V of M minus V of S. This is actually quite simple. All we have to do is find what V of M is and V of S is. So we see the M is directly on this 40 equipotential line. That means the potential at 40, the potential at M is 40. So we write 40 down here, minus the potential at S. So you will notice that S is right in between the 10 and the 0 equipotential lines. So 5 volts would be the value of V of S. 40 minus 5 is simply 35. So that was part D. For E, they give us a charge Q equals 5 times 10 to the negative 12th coulombs. And they want us to find work from this. Now, work is actually one of those formulas that's not on the equation sheet, so that means sadly that you have to memorize it. And that is that work equals negative Q delta V. Conveniently, we already have Q, which is, of course, 5 times 10 to the negative 12th. Delta V, on the other hand, we have to look at the 2 points in question. So in this case, we are looking from point M to point R. Though M and R seem quite far away, this is simply delta V. So we actually have to look at the potential at M and the potential at R. M, of course, is directly on the 40 equipotential line. So M is 40 minus R is on the 30 equipotential line, so that means the potential of R must also be 30. Delta V, therefore, is 10. So work equals negative Q delta V. Oh yes, this. Anyways, work equals negative Q delta V. I screwed up over here. This should be negative 10, and 30 should be flipped with 40, because you are changing from 40 to 30 in a negative direction. So delta V actually should be negative 10. That's my bad. So all we have to do now is just simply plug in our variables. So work equals negative 10, negatives cancel of course, times Q, which is 5 times 10 to the negative 12, times 5 times 10 to the negative 12. And that simply should be 5 times 10 to the negative 11th work. And that is our value for work. Finally, we have part F, in which they ask if the charge of 5 times 10 to the negative 12 removed from N to point S and then to point R, how would E be? Well, would the answer to E be different? And if so, how? Now, we have to look at this formula, W equals negative Q delta V. So the only thing really changing is actually the delta V. But that would actually moving it from point S to point R would not change V at all, because you would simply go in a large negative direction from M to S, and then you would go from S to R. Thus, the net change in potential from N to R is unchanged. Therefore, this answer should be the same for part F.